Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Before we begin, a note from our sponsor. I'm Richard Jacobs, Executive Director of the nonprofit Finding Genius Foundation and host of the Finding Genius Podcast. In late 2016, I was rear-ended at 65 miles an hour by a truck on the highway, which sent me off-road into a ditch. The impact of the collision gave me a concussion and other injuries. At the hospital, a CT scan showed that I had thyroid nodules, which turned out to be cancer. It was then, when I had a biopsy of my neck, that I realized even if I was a millionaire, I wouldn't want a second or a third biopsy due to the pain and the invasiveness of it. And appointments at that time for thyroid experts were 3 to 6 months out. And I was worried about dying now, even if that was irrational. So because of this, I've decided to raise money to conduct a literature review on steroids, on the causes of anxiety and depression, a condition that affects well over 50 million people in the United States and hundreds of millions worldwide. Our goal is to create a codex, a guide that reveals all possible treatments for anxiety and depression for people that live with the condition, or for loved ones that have it, as my wife and my son do. To find out more about our fundraiser, visit findinggeniusfoundation.org and click on Current Initiatives. And now, to our guest.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. Go to findinggeniusfoundation.org to check out our current initiative to study anxiety and depression and create what we call a codex, or a overview of every possible treatment known for those conditions. Today, my guest is Ryan T. Glasser, Ph.D. He's an associate professor at Tulane University, part of the School of Science and Engineering. We're going to talk about physics and quantum optics. So, Ryan, thanks for coming.
Thank you so much for having me, Richard. Really looking forward to it.
Yeah, tell me about your research.
Yeah, so our research broadly involves quantum technologies, and more recently, over the last 5 or so years, a lot of artificial intelligence and machine learning as applied to quantum technologies, really. And the main tool that we use in our research is quantum optics. So really generating quantum states of light to use in quantum applications.
So, all right, what does that mean, quantum optics? What happens to light? How is it quantized? Is it by frequency, other methods? And then we'll go into what you can do with the quantum optics of it.
Sure, yeah. So by quantum optics, we really mean exactly what you just said, is quantized light. So really thinking about light in terms of things like photons, as opposed to prior to the quantum revolution in the early 1900s, people mostly thought of light as behaving like a wave. So really we mean the sort of air quotes particle-like properties of light, which we loosely refer to as behaving like photons. And when you have to describe light as behaving like a particle, then some interesting things can happen. And you can have effects that you can't have if you are just sort of thinking classically, that is, when light behaves like a wave.
So, what kind of effects, what kind of quantum effects occur in light?
Yeah, sure. So one really good example is lowering noise in any kind of system where you use light to make measurements. So prime example, I guess, of this is in LIGO, which I don't know if you're familiar with it, but it's a big, there are two of them. They are very large measurement devices, like kilometers long, shaped in an L, actually. And their goal is to try to measure and detect gravitational waves. And they detected them recently, and a bunch of folks won a Nobel Prize a few years ago for gravitational waves and their detection. And they have to make ridiculously sensitive measurements. So they basically shoot a laser beam down a really long hallway, and it bounces back off of a mirror, and then they measure it. That's sort of the basic gist of it. And what they're trying to detect is a really, really, really small movement of that mirror. That is the length that the laser travels down that hallway is shifted when a gravitational wave passes through. And that amount that it's shifted by, I don't know the number, but it's ridiculously tiny. And so LIGO is a huge effort, and they were actually successful in measuring these gravitational waves. But what you can do is, in addition to just using a laser beam, which a laser beam, by the way, is sort of the most classical kind of light that you can have. That is, it behaves sort of, loosely speaking, I guess, most like a wave. So what they can do is, in addition to using lasers, they can inject quantized light or quantum light into their system and then lower the amount of noise that their measurement measures, and therefore you can pull out a signal easier if your noise is lower. So that's one really useful example.
Well, one quick question. So in this interferometer, so the laser light, what happens to it when a gravity wave passes through it? Does it stretch its wavelength, or like what does it do to it?
It changes the distance, like the physical space distance that the light has to travel. So it's an interferometer, exactly as you said. So you can set these things up so that when the light comes back, there's interference and all of the light goes out of one port, and none of the light, or almost none of the light, goes out of another port. And then you can sort of make these kinds of measurements and detect the length of the hallway that you're sending this laser beam down has changed.
Okay. So, well, I guess, I don't know, like, are you able to explain maybe more deeply, the physics of what happens when, what does a gravitational wave look like versus other waves, other electromagnetic waves? Is it fundamentally different? And like, what happens to the light when this happens?
Oh yeah. So I am in no way, shape or form a gravity wave physicist. I just know that they use interferometers to detect these waves, and the gravitational waves, as far as I understand, actually distort space, right? So the length, so you can imagine taking a laser pointer and shooting it down to a mirror that's a mile away, and then it bounces off the mirror, comes back to you. You can maybe measure how long that takes, right? And then if the mirror has moved by some amount, then it takes a little bit longer or a little bit less amount of time to return, right? I don't think they use any kind of time of flight measurements, but you can set up an interferometer, and in any kind of measurement like this, you have some amount of noise. And I guess what I was trying to get at with the quantum optics part of it is that you can make use of quantum states of light to lower the noise in that kind of situation, and therefore your signal is easier to pull out.
Okay. And you were going to give another example?
Yeah, another one that I can speak more to is what is called quantum imaging. So prime example that I like to give is from the movie Top Gun. Have you seen Top Gun?
A long time ago, probably when it first came out, but I've seen clips of it since.
Excellent. Well, anyway, there's a scene in the movie where the main fighter pilot, right? The movie, for those of you who might not have seen it, is all about fighter pilots, basically. And there's a scene where the fighter pilot is flying in, I guess, enemy airspace, and he's looking at his radar, right? We probably are all familiar with what radar from the 1980s looks like, where you have, a little green screen with a thing that moves around in a circle. And then if something appears on the radar, you get a little blip, right? So he's flying in his jet and he sees a blip appear on his radar. And he says, oh no, there's a bad guy jet, right? Somewhere off in the distance in front of me. And so he flies closer, and then he sees that, oh, actually there's two blips that are just very close to each other. Oh no, there's actually two enemy fighter jets, right? And then he continues to get closer and finds out that it's actually four, and oh no, now this is a big problem, right? I don't know if I can put up a good fight against four enemy pilots as opposed to just one. So in radar like that, the resolution, that is the ability to differentiate between whether or not it's just one blob far away or if it's actually many blobs close to one another very far away, that resolution is fundamentally limited by classical optics. So nowadays, people use laser radar instead of radio wave radar, which gives you
it's a much higher frequency, and you can differentiate smaller features.
Exactly. Yeah, exactly. The resolution is much higher. That's right. But you're still fundamentally limited by the wavelength that you're using for your laser. And so if you were to replace the laser with quantum light, then you can enhance that resolution by significant amounts and be able to see farther away that, there's actually four objects very close to each other, for example. And that's quantum imaging.
So what does that mean? What are you doing to the light to make sure that it's quantized in the way you want it? The laser, again, supposedly emits with, given the uncertainty of it, but it emits in the, just about the same frequency. The photons are all about the same frequency, same energy. What are you doing to light that's different?
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
It's really, I would say, in the way that you're generating the light. So, for example, the way that we generate our quantum sources of our quantum light in the lab is by a nonlinear optical process, which is called 4-wave mixing. And what that really is, the big picture is 4 waves or 4 photons are involved. And we take a specific kind of atom and we shine a very intense laser into it. And then a pair of photons are destroyed by interacting with the particular atoms. And at the same time, you create a pair of photons that shoot off in 2 spatially separate directions. But you're creating these photons in pairs, so they're highly correlated with one another. And you're really creating them in pairs, but together one at a time. So it's
You mean they're entangled? Like one of their states is entangled?
Yes, they can be entangled depending on how you set it up. And otherwise, you can set it up so that they're quantum correlated with one another, which is to say, if I measure one of these photons, then I know with more certainty than classical physics allows me to tell you that there's the other photon in the other spatial position.
Well, you're saying this method, by stimulating the atom in this way, reliably creates photons that are more exact in their energy and their frequency than a laser would create.
Yeah, in some sense, yes. Really, they're created with more certainty in pairs than you would be able to otherwise create.
Okay.
If that makes sense. So if you can kind of imagine, I have 2 beams of light, right, going off in 2 different directions. If I were to put a detector and measure the intensity of each of those 2 beams and then subtract one from the other, if I had a laser and I split it as well as I could do 50-50, so that half of the laser light is going onto one of those detectors and half of the laser light is going onto the other detector. If I could do that as perfectly as I can using laser light, and then I subtract those from each other, you should on average get 0, right? Because you're splitting it 50-50, right? The problem is with classical light, there's some amount of noise that you would then have. So at any given time, you don't necessarily measure 0, but you have fluctuations about 0. Right. In the example that I mentioned of generating these, let's call them twin beams, if you were to perform the same experiment, then you would be much closer to 0 in terms of the noise.
Okay. How much, I guess I'll say quality of light, is the fidelity that much more than any given laser? Like how much less uncertainty is there? How much better is the quality of light?
Yeah, well, so noise reduction would be, I guess, the way we would speak about it typically. And you can pretty easily get factors of, 4 reduction in noise. And then people consistently can get reductions by a factor of 10, for example, in your amount of noise in those kinds of systems. And people have gotten even higher by putting lots of effort into it, trying to get even higher. But, pretty easily you can get factors of 4 to 10.
So I can see for a macroscopic system, like identifying, fighter jets in the airspace, I'm sure it helps that. But what about tiny systems, on the quantum scale? What if you're trying to resolve stuff on, tens of nanometers level? Can this be used in other applications, like to help, let's say, electron microscopes, or to take microscopy further, or to do any measurement in general more accurately?
Yeah. So the answer is yes to everything you just said. Absolutely. And microscopy is another prime example of where this would be useful. Another very good application is in medical imaging. So if you're using a laser to, do these kinds of imaging schemes, one way to increase the resolution is to increase how much laser light you're using. So turn up the power, basically. And that's kind of fine and dandy if you're thinking about trying to image a jet or something, right? But that can be problematic if you're shooting a laser into a biological system, right? You don't want to burn something you're not supposed to burn. So you're sort of fundamentally limited in that case to, how much power you can use in that kind of application. So that's a sort of a prime application for these kinds of quantum optics systems.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
Yeah, do these require high energy inputs and they produce like high energy photons, or can you tune it down where it's you can control the energy of the resultant photons?
So it really depends on the system that you're using, but I think that all of the ones that I'm familiar with at least are nonlinear. So they require a decent bit of, it really depends, but they're mostly nonlinear effects. So you can get more of this quantum state of light as you turn up the amount of, for example, laser in the four-wave mixing that I mentioned. Turn up the four-wave mixing laser that you're shining into it, and you get more of these pairs of photons out non-linearly as you increase the input laser power.
But the sweet spot for the system, is it at lower energies or really, really high energy, or it can be tuned any way you want it?
It can, for the most part, be tuned over, I would say, a pretty wide range. I mean, we're kind of limited, for example, for our research, we're limited into how much laser power we supply into the system. So we buy a commercial laser system and it's limited to some amount of power output, and that sort of is the limiting factor in practice usually. Yeah.
Would this be useful in quantum computing, for instance?
So there certainly are folks that are looking into photonic quantum computing, and these kinds of quantum optics states are then useful in that scenario. So we don't really do any photonic quantum computing, but that certainly is one of several routes of, research. And now I would say development. There certainly are companies that have been formed in the relative recent history using quantum optics, light sources for quantum computing, amongst other approaches to quantum computing. I don't know which one will end up being the best down the road, but that is one approach for sure.
What do you think would happen if you got another order of magnitude improvement on the uncertainty of the photons you're producing? What would you be able to do?
That's an excellent question. I think that probably a lot of the proof of principle kinds of experiments that folks have done would be able to be transitioned a little bit easier into products and actual, applications outside of the laboratory environment. That'd be my guess.
Okay. What is your favorite application of this kind of, this photon production and this optics? What are you using it for? Or if not yet, what do you want to use it for that you're going for?
Quantum communication is a big one. We're using light. So we're involved in a lot of free space optical communications, both classical, that is just basically using laser light to communicate through free space, one party to the other, as well as quantum communication. And so that's, for us, a big application. And we've been working with a lot of folks to try to sort of enhance that by using machine learning, actually, or artificial intelligence, in order to improve the efficacy of these free space communication systems. And so NASA, for example, currently is looking to go away from, or not necessarily go away from RF communications, but they're looking into the feasibility and how well it'll work by using laser-based free space optical communication. So, sort of from point to point, from satellite to the ground, directed kind of laser communications. So, we're trying to improve that. And then the next step beyond that would be replacing it with quantum communications, using quantum states of light to communicate.
Yeah, I don't mean to belabor it, but how does a normal laser work for listeners? And then how does your version of the laser work? Can you get into like a side-by-side comparison of them, just so it's a little bit more clear?
Yeah, sure. So I would say the biggest differentiator between these kinds of classical communication. So first of all, the simplest sort of classical free space laser-based communication system you can have would be what's called on-off keying. And that is just to say, in any given time slice, do I measure at my receiver there is a laser pulse or there is not a laser pulse? And that's, a bit, call it a bit 1 or a bit 0, right? And then the transmitter just sends strings of pulses that are either pulse on or pulse off in a given time bin, and you can communicate and send bits that way, right? That's sort of the most fundamental, or the simplest, I guess, free space communications or communications protocol that exists in general, I guess. But in quantum communications, the big differentiator is that you can generate secure keys between the two parties involved, and you can detect whether or not someone was eavesdropping on your communications channel. And so the ability to detect an eavesdropper and to securely generate cryptographic keys between the two parties is really what sets quantum communication apart from classical communications and makes it extra useful.
Well, how, is it working? How close are we to be able to do quantum communication? I guess I've heard that the Chinese have demonstrated this supposedly to send information over long distances that is supposedly incorruptible.
Certainly, yeah. So there was an experiment indeed that demonstrated that from a satellite to two different ground stations on different portions of the Earth relatively recently, just a handful of years ago. So that was a sort of a proof of principle experiment, which was wonderful. So quantum communication, I would say, in my opinion, probably is the most mature of the quantum technology applications. So I would say in the relative near future, we should start seeing quantum communications networks popping up.
Oh, are there any downsides to quantum communication networks? Are they, slower? Are they more error prone? It sounds like they're uninterceptable, but are there any downsides to it?
Yeah, I think one big downside right now is that technologically speaking, they're just sort of more difficult to engineer. Beyond that, right now, they're probably slower in terms of communicate and bandwidths that you can, the rate with which you can transfer information is slower than using classical optical communications. But I suspect all of those will be engineered away in the future.
Okay. Any other applications that you're interested in, but maybe you don't have time to pursue, but would be interesting that people hear about, or other ones that you are working on?
Quantum sensing is another big one. I guess I would say it's another application of using quantum optics. So, to really any kind of application where you use light to make a measurement on something, you can typically use quantum states of light instead of classical states of light in that scenario and lower the noise. So anytime you lower noise, it's sort of a good thing, right? Because then your signal to noise ratio goes up and whatever you're trying to measure becomes easier to see.
It is an elementary question, but what is noise versus error? Is it just the same thing, just with different terms, or is it fundamentally something different in the system?
Well, for us, for my purposes, when I say noise, I really mean fluctuations in terms of your measured signal, right? So, in LIGO, for example, I guess you are measuring the intensity of light out of one of your ports of your interferometer. And if you're using a laser, then a laser has inherent into it some fluctuations that depend on the scale with the square root of the number of photons that are in your laser at a given time. So you can reduce that noise. That's the kind of noise that I mean in this sense. You can reduce that noise by using quantum states of light.
Noise versus error versus like Heisenberg uncertainty, uncertainty, position or momentum or whatever it is in a system. Are those all facets of the same thing, or are they different?
Well, I'm really glad you asked that, actually. So the noise and the uncertainty principle are sort of very related in this context, actually. And what we typically do when generating these quantum states of light is reduce. So the Heisenberg uncertainty principle, right, is given two specific properties of something, say light, right? You can't know both of them with a certain amount of precision at the same time. So what we can do with quantum optics is sort of tweak that, where we increase the amount of uncertainty in one of those two properties of light that we're interested in, while at the same time decreasing the uncertainty in the other property, such that when you multiply the two together, you still obey the uncertainty principle, but you can sort of tweak the system so that the noise in the thing that you're actually trying to measure is lower than you would get when using classical. So the noise and the uncertainty principle are very much related in that sort of context. Yeah, that's an excellent question.
Well, like in the systems that you talked about and the ones you're working on, which parameters is it more important to reduce noise or error, but which ones suffer as a result and does it matter? Or there are variables that, you really don't care about based on the application. And thankfully you could like kind of throw all the garbage or all the uncertainty into those variables and not care about it much. And you can hone in on the ones you.
Yeah, so it's very much the latter of what you just said. Basically, we can, in terms of the examples I've been giving, basically what we do is lower the uncertainty in, for example, the intensity of the light, while sort of loosely speaking, increase the uncertainty in the phase. And so if you're making a measurement that relies on measuring the intensity, then you sort of win in that case, right? If all you care about is measuring, or if all your system cares about is measuring intensity, then if you can lower the noise in that variable, then you win. You come out ahead.
Are there systems that, let's say, it would flip-flop back and forth incredibly quickly between measuring, let's say, intensity and then phase, and intensity and then phase? And, if you did this, then you're able to switch back and forth, let's say 1 trillion times a second. Would that be a way around getting the data that you want from multiple parameters without, falling into, again, massive uncertainty? Could you have a system that, again, like goes between these two states and therefore gives you the info you want?
Probably in principle. I'm not familiar with anything in practice. We can sort of tweak which variable or which property that we're sort of squeezing the uncertainty in or lowering the uncertainty in. And so while we can change that, typically not necessarily maybe difficult, but it's kind of slow.
Okay. I mean, do you think a system like that, if it existed, would be very useful if it could switch that fast? Or would we run into other problems? And, I know it depends on the application, but just as a thought experiment, do you think something like that would be useful?
Yeah, I would imagine that it would be useful. I can't off the top of my head think of an application specifically, but I imagine that being able to switch what property that you're lowering the uncertainty in very rapidly would probably have some applications. Yeah.
Okay. I'll throw one more thing at you. I heard about squeezing lights or optical tweezers, or what is that? Can you speak to those things and explain what they are? I heard it in the news recently.
Sure. So I can certainly speak to squeezed light very briefly. Just say high level optical tweezers. Optical tweezers in the field of cold atoms is using laser light to slow down, therefore cool atoms. And so optical tweezers are sort of one route of using laser light to trap or slow down atoms. Therefore, I guess that's probably where the tweezer name comes from, sort of grabbing atoms and holding them still. I don't do any of that, but it's a very, very interesting field, cold atoms, and it's enormous. And that's one route towards making quantum computers, actually. But with respect to squeezed light, that's actually what we are generating when I've been talking about lowering the uncertainty in specific properties of light. We call it squeezing. We're squeezing the uncertainty in a given parameter.
I see what you mean. This is kind of related to what I asked you before, if you can get an order of magnitude more precision, but what if there was no uncertainty principle and you were able to get exact intensity or exact, frequency or phase or whatever you wanted to get? What could you then see that we can't see right now?
That's an excellent question. I mean, all kinds of things would become visible, I guess I would say, in terms of measurements, because you could effectively, in that case, reduce the noise down to zero. So yeah, that would basically make a whole lot of measurements and systems just much more effective. Probably would be my guess. For example, LIGO would probably be able to have measured gravitational waves much earlier in LIGO's existence, and then things like laser radar would have hugely improved resolutions and things like that.
Yeah, how good is laser radar right now? Like, what's the the feature size it can go down to discriminate, and how far away?
I don't know the answer to that. I have a distinct feeling that it's very good because you can use optical wavelengths, which are sort of hundreds of nanometers long, right? But whatever that, and it certainly depends on how far away you are, right? As you go farther away, things become harder to resolve just in general. But certainly what I can say is whatever that current resolution is, if you replace the classical light source with a quantum light source, then you can get an n order of magnitude improvement, sort of current quantum optics technology.
Gotcha. Okay. Well, very good. Well, Ryan, what's the best place for people to find out more about your work? Where can they go?
Well, one really useful resource is the archive, arxiv.org. And then there's a quantum physics section. And this is just a free repository where researchers upload papers. And so there's no fee or anything to access them. And that's an excellent resource that researchers use pretty much on a daily basis, I would say. Otherwise, for stuff that's more specific to our research, certainly our group website be a place I could point folks to. Our papers listed up there. It's glasser.tulane.edu. Yeah, those would probably be the two biggest ones.
Okay, so it's Glasser with 2 S's.tulane.edu.
Yes, that's right.
Okay, great. Well, Ryan, thank you for coming on the podcast. I really appreciate it.
Thank you so much for having me, Richard. It was wonderful talking to you, and I look forward to more of your work.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.